Hello, hello, welcome back. So today we're going to go to the next problem. We're on week 2 and we're looking at majority element. Let's go ahead and check that one out. Given an array nums of size n, return the majority element. The majority element is the element that appears more than n divided by 2 times. You may assume that the majority element always exists in the array. Okay, what is n divided by 2? Okay, so let's say n was 1, then it's more than 1/2. So it's the only element. And let's say n was 2, it would be more than 2, it would be more than 1. So the count would actually be 2. Here the count would also be 1. So n equals 3. It would be more than 3 divided by 2. It would be more than 1.5. So it would be at least 2. Okay, so if you have 3 elements, well, it would look something like this, right? And then that scales up. So example 1, nums equals this array that has 3 elements. And you see here that it's 3, 2, 3, and 3 it's a 2 out of 3, right? And then example 2, nums is a list with 1, 2, 3, 4, 5, 6, 7, 8. Is it 8? No, it's 7 elements. Okay, so if n equals 7, then it has to be at least 7 divided by 2, which is 3.5. And the count has to be at least 4. Right, so you have, whatever element is at least 4 is going to be your majority element. So here you have 2, 2, 1, 1, 1, 2, 2. Okay, so there's at least 4 2's here. So that's important to know. Constraints: n equals nums.length. 1 is less than or greater to n, so that means n is always going to be at least 1. And then n is smaller than this super large number. And then the nums can be basically a wide range of negative and positive numbers. Follow-up: could you solve the problem in linear time in O of 1 space? Oh, interesting follow-up. Okay, so let's say the follow-up is the next thing that we do. And in the beginning, you're probably going to want to think about how to solve this in brute force, right? Or, not optimized. So you have, if you think about it, a list of numbers, right? Some list. And we're going to iterate through that list, probably keeping some state, right? And one thing that we can do is just keep a count of all the numbers and then take the one that has at least the majority number count. If you already know the length of your list, so let's say this length is 1,000, you know that it has to have at least 1,000 divided by 2, which is 500. So it's going to be more than 500, right? So let's call it 501. So if you have a list of 1,000, anything that has 501 as a count, you know this is the one. This is the majority element. So if let's say all 501, and let's say the majority element is 8, all 501 are in the beginning, right here in the beginning, then we can go ahead and stop counting. We iterate through all this list, get to the end, see 501, you stop counting. And the most simple version is you just count the whole list. No optimization. You don't stop counting. And then you just take the maximum number. Right, and what is the runtime of that? It's O of n, right? You can iterate through the list, keep a counter, and then get the largest number out of that count. So we can go ahead and write, I'm going to write pseudocode here, and let's just see what that looks like in terms of code. Right, so what is nums? So let's say this is the solution, and there's going to be some stages. Stage 1 is create a counter, And stage 2 is get highest count, right? And from the other stuff, we can pretty much figure out what this is going to look like, right? We have a counter object, right? I think we've done something similar to this in week 1, maybe even earlier here in week 2. And then for n in nums, we're just going to count it, right? So I'm going to go ahead and say the current count is the counter. I'm going to get n, otherwise it's going to be 0. And then the new is going to be the current plus 1. And I'm going to go ahead and put that into the counter. Counter at this n equals this new number. I probably wouldn't use the word new in code because, you know, quite often it's a reserved keyword. I'll put a star there just to remind myself not to actually use the word new. So you build a counter and then you get the highest count, right? So highest count, just keep that as a, you know, negative infinity. Make that a float. And then you're just going to go ahead and count it. So for key and value in counter dot items, if the value is larger than highest, then highest is now equal to value, and we're going to return value at the end of it, right? So this is basically all the code that's going to be required, and it kind of, you know, you could see why the follow-up question is what it is. The runtime here is going to be O of n, but the memory here is also O of n, right? The memory scales with the number of characters, although some people could consider this O of 1 if you consider that there's only, oh no, that's, so it would be O of 1 only if you're using letters, right? Because there's only 26 letters in the alphabet. Here would not be O of 1. It scales with n, right? How many numbers do you have? And so this works. You know, you can go ahead and basically code this exactly how it is here. So I'm going to go ahead and stage counter here, and then stage get highest count. And then Python, there is a counter object. You could probably just throw it in there. And then there's a highest count method. You can do this in one line of code in Python, probably. But let's go ahead and do this, you know, if you didn't have that. So counter get and default is 0, and then new count, let's call it is cur plus 1, and then the counter at n is that new count. And then the highest that we're going to see is, go ahead and make that infinitely small. And then for k and v and counter dot items, if this v is larger than the highest, then the highest is now equal to v. And we're going to return v. And this is basically two-step process. We have counter, get the highest count here. Always got to spell your variables correctly. So there's no autocomplete in here. And in some interviews, they'll actually give you a Google Doc, right? And then there definitely won't be an autocomplete in Google Doc. All right. So you're actually, funny. So you're not actually returning v, you're returning k, right? So this is the highest v, right? But you're not returning the highest v because that's actually, you know, I mean, you know exactly why. Because that's just a random count, right? What you want is you want the highest k to be returned, right? And that becomes the k, and then it becomes something that you return. You're returning the highest k. Simple mistake. All right. So this is that simple version that doesn't do the follow-up. All right. Awesome. So the follow-up is, from my memory, the follow-up follows something called Moore's voting. And it takes into consideration the fact that we have here. Right. So imagine you had 1,000 items. The highest one is going to have at least 501. Okay. And what does that mean? That means if you're looking at a list of many and many and many things, there's going to be items that are for, let's say, the majority element. I'm going to make this yellow here. And then there's going to be items that are against, not the majority element. Right? So let's say these are all 8s. These nots could be a 10, it could be an 11, could be a 12, it could be a 50. But for our purpose, there either is or there is not, right? You're either the majority element or you're not the majority element. And if you take a pointer and you go down this list and you count how many of, basically type A or type B are there, right? There's always going to be more type A's than type B. Right? And that matters no matter how you switch it around. You could put this over here. You can put these reds over here. Even if you mix it around, the final count is there's always going to be, and I'm going to use this one as an example, 501 A's, right? And then the B's are going to be whatever, the rest of it, right? And I believe that's where the intuition from this algorithm comes from, is if you take a pointer, you take this arrow, and let's say all the arrow is doing is logging what it thinks is the majority element. Majority question mark, right? But it's really, what am I seeing now? What's the current thing? Well, in the beginning it sees an A, right? It sees an A and it sees one of them. That's great. If it moves to the next one, it sees another A, right? So now it's seeing 2 A's. If it moves to the next one, it's seeing 3 A's. So now it's 3 A's. If it moves to the next one, it sees a type of B, which is a not, right? So it goes ahead, you can go ahead and think, well, let's put that A back to 2. It moves up again. Let's move that A back to 1. It moves up again. And let's move that A back to 1. So basically, as we iterate through this, at the end of it, we're always going to end up with A being the larger number, being the one that's being tracked. So I can hear your skepticism right now. So let's think about it in another case, right? So let's duplicate this, and let's make it red first, right? So in the worst case, all the reds are in the beginning, right? Right. So here you see a B. It's B1, 2, 3, 4, right? You get up to B4. And when you keep going, this will decrement the B's, 1, 2, 3, 4, 5, until you get down to here, 5, where A is 1, A is 2, and then A is 3, right? So as long as we keep this count of what's currently there, well, we know that because the majority element has more than half, that as long as we keep an honest count, the majority element will, at the point where we get to the end, will be the one that's represented in this kind of current majority question mark position, right? So let's think through one more example. In another extreme case, all the A's are in the beginning. And let's say there's 501 of them. All the B's are at the end, right? So what is your count of A's, right? Your A's are going to start at 1, and then 2, 3, 4, 5, 6, 7, 8, 9, up till 501, right? For this example of 1,000 elements. Now, no matter what happens after this, it's only going to be able to decrement it less than 501 times, which is it's mirrored here as well. Whatever happens here, it's only going to be less than 501 times. And it's mirrored here as well, even if it's interspersed, right? By the time you get to the end, because 501 is just so much of a larger number, your current majority element is still going to be an A of some number. In the worst case, it's an A of 1. It's this one right here, right? In the best case, it looks like this, right? It's like an A of 501, right? So that's, for me, the intuition behind Morse voting. So let's go ahead and code that. Well, before we code this, let's just write it into this diagram, and let's think through what the code would do, right? So you have a list, and you want this, I guess, what should we call it? Candidate or majority element question mark current, right? So as we're moving this arrow, we want this majority element to be considered. So in this function solution, we have some idea of a majority element. And let's just start that with the first element. And we have some concept of majority count. And that's going to start at 1, right? And then we're going to iterate through the rest of it. So for I in range 1 starting to the end of the list, basically, right? We're going to do a comparison. So if it matches, right, then just like here, we're going to iterate on the I. So the majority count plus equals 1. Else, if it doesn't match, then majority count is decremented. And when does it switch, right? So let's think about this switch here. So let's think about if it's all class B and then it's all class A. Well, class B will keep going from 1, 2, 3, 4. And then when does it switch? Well, you have something here that's not B, so B goes to 3. And then you have something here, and then B goes to 2. Here, B goes to 1. Here, B goes to 0, right? So, it can switch at the 0. So if the majority count is 0, switch, right? And this is the code. Sorry if that's a little not eligible or legible. So let's think about the code. So the first element is nums at 0. The majority count, we're going to start that at 1 for I in range of 1 to the length of nums. Then if it matches, well, what does matches mean? Matches is not code, but if it matches, we do something else. Let's say we're going to increment, we're going to decrement, and then if 0, we're going to switch. Right. So what does matches mean? The current number is nums at I, and if this majority candidate is the same as the current number, then we're just going to go ahead and increment, right? And if it's not, then we're going to decrement. So we're going to do the mirror opposite here. But then we also need to consider, what if it's 0, right? What if we get to a switch point? We get to that switch point right there. Then if the majority count equals 0, then we want to switch, right? The majority is now equal to, or this majority candidate is now equal to the current number, and the majority count is now equal to 1. And at the end, we're going to return majority, and this is completely based on what we said before. Given 1,000 elements, we divide by 2, there's going to be 501 of the majority element. So whatever ends up in this majority candidate position, no matter if the count is 501 or if the count is 1, it's going to be the correct majority element. And I believe this is the Moore voting algorithm, but you can definitely intuit it. Okay, so runtime's here, 81%, memory's here. It's not going to tell you the time complexity here, but if you think about the memory here, we're just changing these two variables, right? We're not doing what we did before, where we created a counter and did all the other stuff, right? We're not creating this big object. We're just using these two variables. Anyway, thanks so much. It's been a lot of fun. Please like and subscribe. Leave a comment on any question that you want that's not in this order, because I'm just following this order. Go ahead and check this off. Next one's going to be add binary, diameter of a binary tree, middle of a linked list. If you had a comment of another question, I'd go ahead and explore that one as well. All right, see you next time.